You're told you have 2 years to live, 21 years old. Your body fails daily, speech slurs, legs buckle on Oxford staircases. The family doctor sends you for tests at Cambridge, 2 weeks of poking and prodding. They won't say what's wrong, only what it isn't. Not multiple sclerosis, an atypical case. They hand you vitamins. You see in their eyes they don't expect them to work. Most people fold. Stephen Hawking looked at black holes instead. 1963, amyotrophic lateral sclerosis, ALS, motor neurons dying, no cure. Average survival 2 to 3 years from diagnosis. Hawking got the news shortly after his 21st birthday. By the late 1960s, he needed crutches. By the mid-1970s, a wheelchair. 1985, pneumonia, tracheotomy, speech gone forever. He lived 55 years past the diagnosis. His body betrayed him completely. His mind didn't just survive, it rewrote physics. If you value documented physics and cosmology history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from Physical Review letters published July 1st, 2021, confirming Hawking's area theorem through gravitational wave observations at LIGO. Communications and Mathematical Physics, Volume 43 from 1975, where Hawking published the full radiation calculation. And archived proceedings from the Rutherford Laboratory Quantum Gravity Symposium, held February 15th through 16th, 1974, where Hawking first presented his discovery. Now, back to the information. October 1962, Trinity Hall, Cambridge. Hawking begins graduate studies. Supervisor Dennis Sciama, theoretical physicist, once supported Fred Hoyle's steady-state cosmology. By the 60s, switched sides. Big Bang Theory wins. Sciama builds a research group. Roger Penrose arrives. Brandon Carter joins. George Ellis comes. Martin Rees, too. Cambridge becomes the center of relativity research, everyone working on Einstein's equations. Space-time geometry, cosmology, the shape of the universe itself. Hawking's third year at Oxford, 1962 into 63. He's getting clumsy. Falls on staircases for no reason. Speech starts slurring. Father notices during Christmas break. Family doctor refers him to specialists. Shortly after his 21st birthday, hospital tests, 2 weeks of examinations. They don't tell him the diagnosis directly, only what it's not. Not multiple sclerosis, a typical case. Hand him vitamins. He gathers from their faces they expect nothing to work. He expects it to continue getting worse. They expect him to die within 2 years. But Sciama assigns him a problem. Hoyle-Narlikar theory of gravitation. Does universe expansion contradict it? Hawking dives in, depression lifts, he has work, purpose. 1965, October, submits PhD thesis on properties of expanding universes. 134 pages, 24 years old, diagnosed 2 years prior, still alive, still thinking. Chapter 4 proves something crucial. Singularities are inevitable, not just special cases. General conditions guarantee them. If the universe expands, it must have begun from infinite density. The Big Bang wasn't optional. It was required by the math. February 1966. Thesis approved. Hawking becomes Dr. Hawking. Research fellow at Gonville and Caius College. Remains a fellow there for life. The thesis attracts hundreds of requests per month in Cambridge's archives. 51 years later, October 2017, Hawking makes it open access. Free download, anyone, anywhere. The repository crashes from demand. Millions try to download it the first day. He says he hopes to inspire people to look up at the stars, not down at their feet. Each generation stands on shoulders of those before. Newton, Maxwell, Einstein, now Hawking. The singularity work connects to Roger Penrose. 1965. Penrose publishes the first modern singularity theorem. Genuine post-Einsteinian result. Before this, physicists thought singularities were artifacts, special cases, symmetric situations only. Maybe a collapsing star with angular momentum avoids singularity through centrifugal force. Penrose proves otherwise, introduces closed trapped surfaces. If spacetime contains one, geodesic incompleteness follows. Singularities are generic, not contrived. They form naturally. Hawking reads Penrose's paper, applies the logic backward, not gravitational collapse, cosmology, the universe itself. If expansion runs forward, reverse it. Time backward. Everything converges. Penrose's theorem for black holes becomes Hawking's theorem for the Big Bang. Published 1966 into 1967, proves the universe began from a singularity, not steady state, not eternal, a beginning, finite past, infinite density at time zero. 1970 January, Penrose and Hawking published their only joint paper, The Singularities of Gravitational Collapse in Cosmology, Proceedings of the Royal Society of London, Volume 314. Most refined singularity theorem combines their techniques, shows that under very general conditions, spacetime must be geodesically incomplete. Physical observers following time-like paths reach an end or a beginning, finite time. Singularities are unavoidable. This work wins Penrose half the Nobel Prize in Physics 2020 for discovering that black hole formation is robust prediction of general relativity, but Hawking never wins the Nobel. Why? No experimental confirmation of his most famous work. Hawking radiation remains theoretical, too faint to detect. Solar mass black holes radiate at 10 to the negative 7th Kelvin. Universe background temperature is 2.7 Kelvin. The radiation is swamped. Can't observe it directly. Maybe never will. Primordial black holes from the early universe might have evaporated already if they had mass below 10 to the 12th kilograms. None found. The singularity theorems get Penrose the prize, confirmed by observation, gravitational waves, black hole mergers, real data. Hawking's radiation awaits proof. 1970, Cambridge, Hawking's crawling into bed. His daughter Lucy was born days earlier. His body barely cooperates. The simple act takes minutes. Then, mid-movement, a thought hits event horizon, not the colloquial idea, a precise mathematical definition. The boundary where space-time curves so severely that nothing escapes, not even light. He realizes he can define it rigorously using geometry. No fuzzy descriptions, pure math. Student Gary Gibbons later describes this moment. Hawking figured out how to mathematically define a black hole. Not colloquially, precisely. Within days, he proved something shocking. The area of a black hole's event horizon can never decrease. Never. You throw matter in, the area grows. Two black holes collide. The new horizon must be bigger than the combined area of both. This is Hawking's area theorem, 1971. 50 years later, July 1st, 2021, physicists at Cornell, MIT and elsewhere confirm it for the first time using real gravitational waves detected at LIGO. The signal GW150914, two black holes spiraling inward, they merge. September 14th, 2015. Researchers calculated the total event horizon area before and after. The result held with 95% confidence. The horizon area did not decrease, but there's a problem. Entropy. In thermodynamics, entropy never decreases in a closed system. The second law, everything trends toward disorder. Hawking's area law looks identical. Black hole area only goes up. Entropy only goes up. The math mirrors perfectly. But Hawking and his colleagues insist it's just an analogy. Formal, not real. Black holes have no temperature, no entropy. They're simple objects defined by three numbers: mass, charge, spin, nothing else. The no-hair theorem. Then comes Jacob Bekenstein. 1972. Graduate student of John Wheeler at Princeton. Bekenstein doesn't accept the analogy. He argues black holes do have entropy. Real entropy. Proportional to horizon area. Published in Physical Review, D Volume 7, errs April 15, 1973. His reasoning hinges on information. Drop matter into a black hole and information vanishes. The visible universe loses entropy. That breaks the second law, unless the black hole compensates. Bekenstein proposes the area itself is entropy. When mass falls in, area grows, entropy is saved. Hawking hates it. He wants to prove Bekenstein wrong. For months, he attacks the idea. Black holes absorb. They don't emit. Temperature needs emission, thermal radiation, black holes are cold, dead. That's the classical picture from general relativity. But Bekenstein keeps pushing. The analogy must be real. The math demands it. 1973, September, Krakow, Poland, International Meeting on Cosmology. Hawking meets Yakov Borisovich Zeldovich, Soviet astrophysicist, nuclear weapons architect, also studied black holes. With him is his PhD student Alexei Starobinsky. They've discovered something. Rotating black holes shed energy by creating particles. Exceptional circumstances only. The quantum uncertainty principle. Pairs pop into existence near the spinning horizon. The rotation tears them apart. One escapes, the black hole loses mass. Published in Soviet Physics. JETP Volume 34 from 1972. They convince Hawking to investigate. Look at empty space near the event horizon. Use quantum field theory. Hawking returns to Cambridge. His body deteriorates. Speech harder to understand. Only family and close friends can interpret him. By the late 70s, strangers need a translator. But his mind operates differently now. He can't write equations easily. Hands fail, so he visualizes. Kip Thorne at Caltech later describes this. Hawking manipulates images in his mind. Ribbons, curves, cubes, spheres, topological transformations, a coffee cup morphing into a donut. His flowing mental images give insights nobody else finds. He sees equations as geometry. Werner Israel later compares this to Mozart composing entire symphonies in his head. The disability becomes the method. Between September and December 73, Hawking works through the problem. How does quantum field theory behave in curved spacetime? Not flat Minkowski space, curved, near a black hole, the Schwarzschild geometry. Simplest case, non-rotating, no charge, just mass warping spacetime. He can't use pencil and paper easily anymore, so he builds the calculation mentally. Geometric shapes, light cones tilting, null geodesics tracing paths, virtual particle pairs appearing everywhere in the vacuum. But near the horizon, something changes. The horizon itself isn't special locally, and someone falling through wouldn't notice. No wall, no barrier, just crossing a mathematical surface, but globally it matters. It separates inside from outside, forever. And quantum field theory cares about global structure. The vacuum isn't empty. Quantum fluctuations, Heisenberg uncertainty, energy borrowed briefly from nothing. Particle-antiparticle pairs pop into existence. Normally, they annihilate immediately. Energy returns. But near the horizon, the curvature tears them apart. One particle falls in, one escapes. The particle that falls in carries negative energy relative to the outside universe. This sounds strange, but it's allowed near a horizon. The escaping particle carries positive energy. To an observer far away, it looks like the black hole emitted a particle. Radiation. The negative energy particle reduces the black hole's mass. Energy accounting balances. The black hole pays for the escaping particle by losing mass. Over time, it shrinks. Eventually, it evaporates completely. December 1973. Cambridge. Quiet study desk. Hawking works through the quantum field theory calculations mentally. Not rotating black holes like Zeldovich studied. All black holes, even non-rotating, non-charged ones. The simplest case, Schwarzschild geometry. He applies quantum mechanics to curved space-time near the event horizon. Virtual particle pairs constantly appear and vanish in empty space. Quantum fluctuations, everywhere. But near a black hole, the extreme gravity changes things. The event horizon distorts the pairs. One particle falls in carrying negative energy. The other escapes with positive energy. To an outside observer, it looks like the black hole radiated a particle. Energy leaving means mass decreasing. The calculation shows black holes emit thermal radiation, perfect blackbody spectrum, temperature inversely proportional to mass. For a solar mass black hole, 10 to the negative 6th power times the solar mass divided by the actual mass, measured in Kelvin, tiny, undetectable, but real. And it confirms Bekenstein. Black holes have temperature. They have entropy. The area law isn't analogy, it's actual thermodynamics. The temperature T equals surface gravity, kappa, divided by 2 pi in natural units. Kappa equals 1/4m for a Schwarzschild hole. Mass m, the temperature drops as mass increases. Supermassive black holes are colder than the cosmic microwave background. They absorb more than they emit. But tiny primordial black holes would be hot, radiating intensely. If they existed, Hawking realizes something else. The entropy formula. If black holes emit thermal radiation at this temperature, and the area represents entropy, then the entropy S equals 1/4 of the horizon area, A divided by the Planck length squared. The Bekenstein-Hawking entropy formula. Every constant of nature appears. Planck's constant, speed of light, gravitational constant, Boltzmann's constant. This equation unites quantum mechanics, general relativity, and thermodynamics. 3 pillars of physics, one formula. Hawking later says he wants this formula on his tombstone. At his 60th birthday in 2002, after crashing his wheelchair into a wall at age 59.97, he declares he wants the simple formula engraved on his grave. The wish is granted 16 years later. If you value this deep documented history of 20th century physics, subscribe. It's free and supports bringing more content like this to everyone. Comment your city so we know where this story reaches. This script is factual and researched using primary sources, including Stephen Hawking's own 1966 PhD thesis, Properties of Expanding Universes, submitted to Cambridge University and made open access in October 2017. His 1975 paper, Particle Creation by Black Holes, Atoms and Communications in Mathematical Physics, Volume 43. Penrose and Hawking's joint 1970 paper in Proceedings of the Royal Society of London, Volume 314, and the July 2021 Physical Review Letters paper by Isey, Geisler, and collaborators confirming Hawking's area theorem through LIGO gravitational wave data. These are real calculations, real discoveries, documented in peer-reviewed journals. Now back to December 73, but there's a problem. Hawking set out to disprove Bekenstein. To his surprise and annoyance, his own calculations support Bekenstein's idea. He's proven himself wrong. This happens often with great scientists. They chase one answer and discover another. The mistake becomes the breakthrough. February 15th through 16th, 1974. Rutherford Appleton Laboratory, south of Oxford. Symposium on quantum gravity. Friday and Saturday after Valentine's Day. Hawking's wheeled into the meeting room. 32 years old, diagnosed 12 years prior, confined to wheelchair but mind intact. He presents his results. Black holes radiate. They evaporate. They're not eternal prisons of light. They leak. The title of his upcoming Nature paper already chosen. Black hole explosions? ? Intentional? Provocative. Challenging everything physicists thought they knew. The chairman of the session, John Taylor from King's College London, stands up. Sorry, Stephen, but this is absolute rubbish. Nobody believes him. He's threatening to overturn everything. Black holes defined by their inability to emit. Now Hawking claims they glow. Some attendees, like Martin Rees, quiver with excitement. Everything has changed, Rees tells people. Others reject it outright. Dennis Sciama, one of the conveners and Hawking's PhD supervisor, sits stunned. He will later call the discovery a work of genius, in my opinion. Later still, he'll tell interviewers this was the most beautiful paper in the history of physics. Hyperbole, perhaps, but the shock is real. The paper challenges the foundations. No going back. Hawking distributed preprints before the conference. Late December 73, sent them out before Christmas. Bill Unruh at University of British Columbia received one through Abe Taub and Vince Moncrief, Taub's postdoc. Unruh had been working on similar ideas. Rindler space, accelerated observers, showed that acceleration produces thermal radiation. The Unruh effect got their result before Hawking, but didn't publish until 76. To his disgust and future chagrin, as he later admits, Hawking got there independently. Published first, gets the credit. That's how science works. First to press. 2 weeks later, March 1st, 1974, Hawking publishes a short paper in Nature Volume 2, 48. Black hole explosions? 2 pages. He describes the radiation mechanism. Virtual particles at the horizon. One escapes, one falls in, the black hole radiates. For primordial black holes with mass less than 10 to the 12th power kilograms, formed in the early universe, they would have completely evaporated by now. None found yet. The discovery makes immediate waves. Royal Society takes notice. Hawking writes a longer complete description. Submits to Communications in Mathematical Physics in March 1974. The journal loses his manuscript. A year passes. He inquires. They ask him to resubmit. Published finally with submission date erroneously listed as April 1975. Volume 43. Particle creation by black holes. The full mathematical treatment. By then, the discovery is already accepted. Hawking's elected Fellow of the Royal Society, 1974. One of the youngest ever. Few weeks after announcing Hawking radiation, now comes the nightmare. The information paradox. If black holes radiate and evaporate completely, what happens to the information? Every particle has properties: spin, mass, charge, position, information. When matter falls into a black hole, that information crosses the horizon. Then the black hole radiates thermally. Pure thermal radiation carries no specific information, just heat. After the black hole evaporates, only featureless thermal gas remains. The original information is gone, destroyed, lost forever. This violates quantum mechanics. Fundamental principle: unitarity. The wave function evolves deterministically, reversible. You can reconstruct the past from the present. Information is never lost, but Hawking's calculation suggests it is. The radiation depends only on mass, charge, spin, not on what fell in. 2 completely different stars collapse to identical black holes, same mass, same properties. They radiate identically. They leave identical thermal remains. You can't tell which star it was. Information lost. The quantum state of the universe becomes mixed. Pure state becomes mixed state. Forbidden by the laws of physics, unless those laws break down at black holes. Hawking frames this as the breakdown of predictability in gravitational collapse. Paper after paper in the mid-70s, he argues microscopic irreversibility, not just thermodynamic, but fundamental. Black hole evaporation isn't unitary. Quantum mechanics breaks down at black holes. Most physicists disagree. Tom Banks at Rutgers later explains the contradiction leads to equations massively inconsistent with experimental facts. String theory models show clear information preservation. But how? Where does the information go? How does it escape? The radiation looks perfectly thermal, no correlations, no structure, just heat, yet information must escape somehow. Otherwise, quantum mechanics is wrong, or gravity is wrong, or both. 1976, Don Page, Hawking's doctoral student, objects to the paradox on CPT symmetry grounds. Charge parity time symmetry, fundamental physics symmetry. Page argues information must be preserved. Hawking's calculation must miss something, but the calculations are published. The paradox becomes famous. It drives research for 50 years. Thousands of papers, dozens of proposed solutions. Addis as CFT duality discovered partly to resolve it. Holographic principle emerges from thinking about black hole entropy and information. Juan Maldacena's 1997 conjecture. Anti-D Sitter space in 5 dimensions. Conformal field theory on 4-dimensional boundary. Gravity emerges from quantum entanglement. Information preserved in the boundary theory. Black hole interior encoded on the surface. Holography. Page develops another crucial insight. The Page time. The moment when the black hole is half evaporated. Before this, entanglement builds between the radiation and the black hole interior. After this, entanglement must transfer to correlations within the radiation itself. Information starts escaping. The entropy of the radiation first increases, then decreases. The Page curve. Deriving this curve becomes the test of any proposed solution. String theory manages it for certain special black holes. Supersymmetric extremal cases. Andrew Strominger and Kamran Vafa, 1995. Count the microstates using D-branes, get the right entropy, match Bekenstein-Hawking formula exactly. First-time statistical mechanics reproduces black hole entropy from counting states. Huge breakthrough. But only works for special cases. Ordinary Schwarzschild black holes remain mysterious. Some believe the information escapes gradually through subtle correlations in the Hawking radiation. The Page time. The moment when more than half the black hole has evaporated and information starts leaking. Others propose modifications to the horizon structure. Firewalls, fuzzballs, no smooth horizon. Instead, structure at the horizon scale. Recent work 2023. Physicists develop lossy quantum codes. Show information can be preserved even as the black hole evaporates. The radiation carries information through quantum entanglement, not destroyed. Encoded. Other researchers propose quantum hair, soft degrees of freedom at the horizon. Store information without violating the no-hair theorem. Published Physics Letters PA. Resolves the paradox, potentially. Hawking's own final attempts before death in 2018 involve soft hair surrounding the black hole. A halo storing information. But the paradox itself, the challenge Hawking posed, pushed physics forward. By finding the contradiction, he forced generations to confront how quantum mechanics and gravity interact. The information paradox remains active research. Loop quantum gravity calculates black hole entropy from quantum geometry of the horizon. Gets the right formula, but requires tuning a free parameter. Bekenstein-Hawking formula emerges from the quantum states of the horizon area. String theory derives the entropy for supersymmetric black holes. Andrew Strominger and Kamran Vafa, 1995. Count the microstates. Get the right number. Bekenstein-Hawking entropy confirmed from first principles. Analogs in the lab. Can't detect actual Hawking radiation. Too faint. Solar mass black hole radiates at 10 to the negative 7th Kelvin. Far below cosmic microwave background at 2.7 Kelvin. Won't evaporate for 10 to the 67th years. Universe age, only 13.8 billion years. But physicists create black hole analogs. Sonic black holes. Use Bose-Einstein condensates. Sound waves instead of light. Fluid flow creates an acoustic horizon. Sound can't escape past a certain boundary. Quantum fluctuations near the boundary produce phonon pairs. One escapes, one trapped. Jeff Steinhauer, 2016, observed thermal phonon radiation, matches Hawking's prediction, entangled pairs across the horizon. 2022, Lotte Mertens, University of Amsterdam, creates analog using a one-dimensional chain of atoms. Electrons hop from position to position. Altering the hop amplitude creates an effective event horizon, interferes with electron wave nature, produces temperature rise matching theoretical expectations. only when part of the chain extends beyond the event horizon. Suggests entanglement on the horizon generates the radiation. Published Physical Review research. Hawking's mental process. How did he do it? Trapped in a body that fails daily. Can't write. Can't turn pages. Visualizes equations as geometry. Sees space-time curves. Light trajectories bending through warped geometry. Mental images flowing. Roger Penrose, collaboration on singularity theorems, late 60s. Proves that under general relativity, singularities are inevitable. Big Bang was inevitable. Black holes form singularities inside. No escape. Physical infinities. Werner Israel compares Hawking's achievements to Mozart composing entire symphonies in his head. The radiation calculation done mentally. December 73. Realization came during the slow process of working through quantum field theory in curved space-time, not writing equations, imagining them, geometric shapes, particle paths, horizon topology, the curvature tensors, the stress energy, all in his mind. His collaborator Gary Gibbons describes the moment in 1970. Hawking's getting into bed takes enormous effort, but during that struggle, the mathematical definition of the black hole horizon crystallizes, not distraction from the disability. The disability forces a different way of thinking. No pencil pushing, pure visualization. Some argue this limitation became his strength. Different neural pathways, different insights. If you value this deep documented history, subscribe. It's free and supports more content like this. Comment your city. Back to the story. Hawking keeps working despite everything. 1975, appointed reader in gravitational physics at Cambridge. 1979, elected Lucasian Professor of Mathematics. The chair Isaac Newton held, one of the most prestigious positions in science. He holds it until 2009, 30 years, all while paralysis advances. By 1985, breathing fails. Pneumonia, emergency tracheotomy, voice gone. Friends build him a computer speech system. Operates at first with a hand switch, later only a cheek muscle. The synthesizer becomes iconic. Robotic voice explaining the universe. 1988. A Brief History of Time. Published, explains black holes, Big Bang, time itself to general readers, stays on Sunday Times bestseller list for 237 weeks, record-breaking. He makes science accessible, appears on Star Trek Next Generation, The Simpsons, Futurama, Big Bang Theory, becomes the most famous scientist since Einstein, pop culture icon and rigorous physicist simultaneously, bets with colleagues. 1974, wages with Kip Thorne about Cygnus X1. Is it a black hole? Thorne says yes. Hawking says no. Insurance policy against his own theory being wrong. 1990, Hawking concedes, lost the bet, buys Thorne a subscription to Penthouse magazine. The bet agreement specified the winner's choice. Another bet. 1991 with Thorne and John Preskill, cosmic censorship conjecture. Roger Penrose's proposal. Can naked singularities exist? Singularities without event horizons? Hawking bets they can't, discovers he might be wrong. New refined wager. 1997, another bet about the information paradox with Thorne and Preskill. Does information escape black holes? 2004, Hawking concedes the information paradox bet, declares he's solved it. Information preserved after all. Not everyone's convinced. The solution involves subtle quantum effects at the horizon, but he hands Preskill a baseball encyclopedia. The terms specified a winner's choice of encyclopedia. Preskill wanted information easily retrieved. Hawking's gesture. Information can be recovered, but in degraded form. 1971 to 2021, 50 years. Hawking's area theorem awaits observational confirmation. September 14th, 2015. LIGO detects gravitational waves. First direct observation. Two black holes colliding, 1.3 billion light years away. Masses 29 and 36 times the sun. They spiral inward. Merge. Create a black hole, 62 solar masses. 3 solar masses converted to energy. Gravitational waves ripple across space-time. Signal GW150914. Physicists analyze the signal. Maximiliano Isi, MIT. NASA Einstein postdoctoral fellow. Matthew Giesler, Cornell. Multiple collaborators. They develop technique to extract reverberations immediately after the peak, the moment of collision, pick out specific frequencies from the noisy aftermath. Calculate the final black hole's mass and spin. Then compare to the parent black holes. Did the area increase? Results published. Physical Review Letters, July 1st, 2021. The data shows with overwhelming confidence the horizon area increased. Area law satisfied with very high probability. 95% confidence. Hawking's theorem confirmed, 50 years after he derived it. Purely mathematical proof now has observational evidence. IC says it's a relief. Result agrees with expectations, confirms understanding of complex black hole mergers. Giesler notes the methods developed for the first merger now test Hawking's 1971 proposition. Putting Einstein's theory to the test, as detectors improve, they'll keep probing gravitational waves, looking for where Einstein's theory might break down. 2018, March 14th, Stephen Hawking dies at home in Cambridge, 76 years old, 55 years past the original 2-year prognosis. His ashes interred at Westminster Abbey. Between Isaac Newton and Charles Darwin, the tombstone formula, S equals K times A over 4 L Planck squared, Bekenstein-Hawking entropy, the equation he wanted remembered, black hole entropy proportional to horizon area, quantum mechanics, gravity, thermodynamics united, the mental process that changed physics, diagnosed young, slow progression, juvenile onset form, extremely rare. Less than 5% of ALS cases start before age 40. Prognosis much better than later onset, but still unprecedented survival. Disease seems to have burned out, plateaued, stabilized eventually, extremely rare. Biological differences in early onset cases, maybe a dozen genetic forms, maybe interaction with aging process. Hawking himself suggested his variety might be vitamin absorption issue. He supplemented daily, minerals, vitamins, zinc, cod liver oil, folic acid, B complex, B12, C, E, diet free of gluten, vegetable oil, no convenience foods, small amount of dairy added later. The care matters. Round-the-clock nursing from 1985. Passive chest physiotherapy. Active and passive physiotherapy to all limbs. Specialized wheelchair. Dragon mobility. Dragon from 2007. Permobil C350 from 2014. Permobil F3 from 2016. Each upgrade maintaining mobility, maintaining independence. He raced the wheelchair around Cambridge, had accidents, broke bones, lived fully, zero gravity flight at age 65, hot air balloon on his 60th birthday, traveled every continent including Antarctica, married twice, 3 children, never lost humor or zest, but the physics, that's what endures. The mental journey from area theorem to radiation to information paradox, each step forced by the math. 1970, defining the horizon. 1971, proving area never decreases. 1972, Bekenstein proposes entropy. 1973, Moscow, meeting with Zeldovich and Starobinsky plants the quantum seed. December 73, Hawking realizes black holes radiate. February 74, announces at Rutherford. March 74, publishes in Nature. 1975, full calculation in communications and mathematical physics. Mid-70s, information paradox emerges. Decades of debate follow. The breakthrough wasn't just calculation, it was vision, seeing what others couldn't. Held in a failing body, his mind ranged across curved space-time, quantum fluctuations at event horizons, virtual pairs torn apart by gravity, thermal radiation leaking from the ultimate darkness, temperature encoded in surface gravity, entropy written in horizon area, information trapped, then maybe escaping, the universe more subtle than anyone imagined. Contemporary physics still grapples with it. How does information escape? Through entanglement? Through soft hair? Through modified geometry? The recent papers keep coming. 2023 quantum codes. 2024 quantum hair resolves information loss. 2025 researchers confirm area theorem through gravitational waves. 53 years after, Hawking derived it sitting in Cambridge, unable to write the equations down. He built the math in his mind, geometric intuition, topological imagination. That's the lesson. Reality hides in mathematics. Equations describe nature at scales we can't visit. Can't touch a black hole horizon. Can't see Hawking radiation. Too faint, too far, too dangerous. But the math predicts it. Hawking's mind, locked in a wheelchair, traveled to event horizons, calculated emission spectra, proved thermodynamic laws apply to gravity's most extreme objects, united 3 theories thought incompatible, found paradoxes that still drive research, the cemetery at Westminster Abbey. The stone reads, "Here lies what was mortal of Stephen Hawking, 1942-2018. The formula engraved below, 1/4 of the horizon area, the entropy, the information. Everything about a black hole encoded on its surface, not its volume, its surface, the holographic principle. Inspired by Hawking's formula, information in three-dimensional space, perhaps encoded on two-dimensional boundaries. Gravity might emerge from quantum entanglement. Space-time itself might be emergent, not fundamental. These ideas all trace back to Hawking's equation. He transformed how we see black holes. Before Hawking, they were eternal prisons. Nothing escapes. After Hawking, they're dynamic objects. They evaporate. They have temperature. They thermalize. They connect quantum mechanics to gravity in ways still being decoded. The information paradox isn't solved, not completely. Different approaches offer different resolutions, but the paradox itself forced physicists to reckon with the marriage of quantum and gravitational physics. Black holes became laboratories for quantum gravity. All because a dying man looked at them with different eyes. 2024, a team in Christoph Kahl at MIT and Ryan Unger at Stanford and Berkeley prove Hawking, Bardeen, and Carter wrong about something. 1973. The three physicists proposed the third law of black hole mechanics. Surface gravity cannot decrease to zero in finite time. Extremal black holes can't form. Kelly and Unger prove otherwise. Extremal black holes are possible. Hawking wrong. Again, like with Bekenstein, wrong but productively. The mistakes inspire better understanding. That's the process. Conjecture, calculate, discover surprise, announce, debate, refine, sometimes concede, always push forward. Hawking did this repeatedly. Area theorem, radiation, information loss, concession on information, extremal black holes. Each step a mental journey through geometric intuition. Ribbons and curves, spheres deforming, light rays bending. Quantum fields in curved space, the visualization others couldn't achieve. Why could he? The disability forced it. No choice. Can't scribble equations, must see them. Geometric shapes carry more information than symbolic manipulation sometimes. Different mode of thinking. Kip Thorne said nobody else could visualize like Hawking. The images flowed, insights followed. Tour de force calculations completed mentally. The wheelchair was an obstacle. It was the condition under which the mind adapted, developed new skills, saw differently. Physics demands different approaches. Some physicists work with equations on paper, Feynman diagrams, symbolic manipulation, algebra. Others visualize. Einstein did thought experiments, trains moving at light speed, falling elevators, geometric intuition. Hawking took this further. Had to. No paper, no pencil. Only mind, only geometric imagination, curves in space-time, light cones tilting, geodesics converging, horizons forming, particles appearing from quantum fluctuations. All visualized, all calculated without writing a single equation. This isn't how most physicists work, but it worked for Hawking. Maybe it worked better. Different pathway to the same truth, maybe a clearer pathway. Less cluttered by formalism, more direct to the geometry underlying reality. Space-time itself, curves and warps. Mass tells space-time how to curve. Space-time tells mass how to move. Wheeler's famous phrase, Hawking saw this directly. Not through equations, through mental pictures of curved manifolds, topological spaces, null surfaces, trapped regions, event horizons, the geometry of gravity itself. Archive holds 10,000 pages of his scientific papers now. At Cambridge University Library. Wheelchairs, speech synthesizers, personal memorabilia at the Science Museum in London. Hawking Building opened 2024 at Science and Innovation Park near London. Houses the National Collection Center. 80% of the museum's object collection, nearly 400,000 items, from Stephenson's rocket locomotive to Apollo 10 command module. From Babbage's difference engine to the first iron lung, and now Hawking's office, preserved. The modified computer, pressure sensors, head-mounted pointer, cheek muscle sensor, communication board. The technology that let a paralyzed man explain the universe. The chair he raced through Cambridge streets. The voice synthesizer that became iconic. American accent. Robotic cadence. Instantly recognizable worldwide. More famous than any physicist since Einstein. Maybe more famous than Einstein ever was. 2011, Google's Zeitgeist conference. Hawking declares, philosophy is dead. Science answers the questions philosophers asked. What is reality? How did the universe begin? Why are we here? Physics provides answers. Math describes being. The equations tell us what exists at scales beyond human perception. Planck scale, quantum foam, virtual particles. Black hole horizons, Hawking radiation at 10 to the negative 7th Kelvin. Information encoded in area, not volume. These aren't philosophical speculations. They're physical predictions confirmed by calculation, observation, experiment. The mental process, that's what this was about. How does a paralyzed man change physics? By seeing differently. Equations as geometry, shapes as mathematics, visualization as calculation. The disability forced adaptation. The adaptation enabled insight. The insight revolutionized cosmology. From area theorem to radiation to information, paradox. 50 years of thinking about black holes, thinking differently, thinking despite, thinking because. His final paper, 2018, published posthumously, Black Hole Entropy and Soft Hair, with Sasha Hacko, Malcolm Perry, Andrew Strominger, proposes soft photon and graviton hair on black holes, carries information, infinite dimensional space of symmetries at the horizon, resolves information loss maybe, preserves Hawking's legacy, still trying to solve the puzzle he created in '74, still pushing. The mind that couldn't turn pages turned space-time inside out. The voice that couldn't speak articulated cosmology's deepest mysteries. The body that couldn't move traveled to event horizons. That's the mental process. Not despite the disability, through it, transformed by it. Hawking's black hole journey is a journey of mind over circumstance, visualization over calculation, geometry over algebra, insight over formula. Westminster Abbey. 1957, Scientists' Corner, Planck's Mark, Darwin, Newton, Faraday, Maxwell, Giants of Physics. 2018, Hawking joins them. The formula on stone, S equals Ka over 4 L Planck squared, black hole entropy. The equation that bridges quantum and gravity. The discovery made in December '73 by a paralyzed mathematician who couldn't write it down, who saw it instead, curved space, virtual pairs, thermal spectrum, temperature, entropy, radiation, evaporation, information, paradox. Reality is stranger than we imagined. Black holes aren't black, they glow, faintly, undetectably. But they glow. The math proves it. Hawking proved it. With his mind, in his wheelchair, in Cambridge, in December 1973, 51 years later, gravitational wave observations confirm his 71 area theorem. The math was right, the visualization was right, the mental process was right. That's how you change reality. You see it differently, even when you can't see at all, even when you can't move, can't speak, can't write. You see equations as geometry. You see black holes as thermodynamic objects. You see radiation where everyone sees only darkness. You see with your mind, and your mind is enough. It was enough for Hawking. December '73, black holes radiate. The equation holds. The tomb reads truth. The mental process endures.